All right, let's work through this. Let's first go ahead and think about it in terms of scratch work before we try to write something up nicely. Like I said, probably the two-step subgroup test is easier here. But really remember, the one-step subgroup test really requires 2 steps, and the two-step subgroup test really requires 3 steps. There's always this 0th step of showing the set is non-empty to begin with. Now, the example last Friday, it was fairly trivial. It was definitely non-empty, but this one's a little less trivial. Why is CA non-empty? Somebody want to give a reason for that? Exactly. The identity commutes with everything by definition of the identity. Therefore, the identity is in C of A, and therefore it's non-empty. We know EA equals AE equals A. Therefore, the identity is in C of A. C of A is non-empty. Actually, I probably should have written this like EA equals A equals AE would have been a better way to write that. To ultimately, in a sense, prove that EA equals AE. But if you look in the definition of the identity, it's there as well. So it's not a real big deal. All right, what's now the first step to do in the two-step subgroup test? Describe it in words. Show and what's that called? One word, starts with a C. Closure, yeah. Well, closure under multiplication. There's also going to be in step 2, closure under inverses. Probably is best in this particular case, not in general, to use a letter other than A, since A is a fixed element here that's given. So say let B and C be in C of A. If C of A is only the identity, which technically speaking it could be, it's possible that C of A, which by the way does have a name here, it's called the centralizer of A in G. And that's the element A, not the word A. I'll put quotes around it. It's possible for the centralizer to be just the identity. That can happen. In fact, we'll see an example here in a minute where it does happen. So let B and C be in the centralizer of A and G. You might want to write a little note to yourself. Certainly in your scratch work, you can write we must show on your proof as well. Maybe you're used to doing that. BC is in C of A. So what does that mean? You have to use the defining condition of what it means to be in the centralizer of A. You got to commute with A. You got to use the fact that you're assuming B and C commute with A. So keep those kinds of things in mind. You need to use the definition of what C of A is, and you need to use the fact we're assuming in this part of the argument that B and C are in the centralizer. They do commute with A. And then once you realize that, it's fairly simple. Think of it like this. Let's emphasize it with parentheses, although parentheses are not absolutely necessary. BC times A by the associative property. Yeah, whenever you use the associative property, you don't actually have to say it unless I explicitly tell you. Although sometimes you do have to verify it. With the matrix example in your homework that you turned in last Friday, technically speaking, matrix multiplication is associative from linear algebra. Technically, that does need proof, but it's a known fact from linear algebra. So there's the associative property. Now use the fact that C is in the centralizer of A by assumption. Now use the associative property again. I guess you should, with a problem like this, you probably should show each one of these steps. You probably should, for clarity's sake, use parentheses like I'm doing. Oops. BAC. And then use the fact that B is in the centralizer as well to write this. And then you use the associative property again. I think I won't take the time to write out a nice proof of this. You know, is this a sentence structure as is? Well, I'd say a little bit more. I'd say, you know, you should say, we know this is true. I guess it's worth saying the associative property here. Again, just for clarity's sake and using the parentheses, just to emphasize that you really do need it. And then, because C is in the centralizer of A, you could write that it equals this. Maybe that could be all part of one sentence. And then you could say about the associative property and the fact that B is in the centralizer, this equals this equals this. Finally, about the associative property again, you get this, which implies B times C is in the centralizer because you've got it commuting with A. Yeah, for a problem like this, for clarity's sake, to emphasize the key points. Yeah, if I put this on the test, I'd probably indicate where you use the associative property, just for clarity's sake, even though it is pretty trivial when you get down to it. And now show it's closed under inverses. We're already assuming, say, B and C are in A. Let's show it's closed under, let's show that B inverse is in the centralizer. Okay, I'll go ahead and rewrite it again. Let B be in the centralizer. Must show, not mush, but must show B inverse is in the centralizer of A. So you got to show B inverse commutes with A. This is a little less obvious. Using the fact that B commutes with A, how do you show B inverse commutes with A? Let's really think of this as some scratch work here. We know B times A equals A times B. What kind of work could you do with this equation to help convince yourself B inverse commutes with A as well? What kinds of manipulations do you have any? I always talk about gut instinct here. You want to develop some sort of gut instinct in this class about what to try, even if you're not sure if it's going to work. Yeah, you want to get the B inverse in there some way. So make it be in there. Of course, you can't break the rules of algebra in doing so. If you do it to one side, you got to do it to the other side. For example, we could multiply on the left by B inverse. I'm going to write equivalencies here, arrows that go both ways because they are equivalent, and that might be worthwhile. And I will emphasize the associative property again. So those two equations are equivalent to each other because to get from here to here, I multiply the same thing on the left of both sides. Actually, to go backwards, to go from here to here, I would really, well, you could think of it as cancellation, cancel the B inverses, left cancellation, or you could think of it as multiplying both sides of this thing on the left by B, even though we're not seeing that there. Probably since I'm not literally, it's probably better just to think of it as cancellation going the other way. Now use the associative property. maybe to write that. I guess I didn't necessarily have to do it on the right. It's helpful to do it on the left because that's E. And so therefore this entire thing is A. So this equation is equivalent to, let's just rewrite this. A equals B inverse AB with, if I write it without parentheses. Is that helpful? I did it on the left. Maybe I should do it on the right too. I multiplied by B inverse on the left. Maybe I should multiply it on the right. And I'll go ahead and put parentheses in like this. So now I multiply both sides on the right by B inverse. And that does it, I guess, doesn't it? AB inverse equals B inverse A. So now how should your proof go? In this case, the scratch work we did, the direction that we did it in from here to here to here to here is a logical progression that you could use for a proof. We know this is true. Therefore, by left multiplication, this is true. By the associative property, this is true. And then by right multiplication by B inverse, this is ultimately true, which is what we want to show. Therefore, B inverse is in the centralizer. And therefore, by the two-step subgroup test, the centralizer of A in G is a subgroup of G. But there are situations where, if I can think of one off the top of my head, where you're trying to show something's true and your scratch work needs to be reversed. The logic of your scratch work needs to be reversed. How can I think of an example? Like showing a certain number solves an equation. Let me say a certain function solves a differential equation, just to think of an example quick. Y equals e to the 2t solves a differential equation, solves this one, dy dt equals 2y. Not everybody's had differential equations. What does this mean? It means the derivative of this function with respect to t, which you can see by looking at it from the chain rule, is going to be 2 times e to the 2t, is indeed 2 times itself, 2 times the function. Verifying this is a solution is easy, but I'm trying to, maybe this is not such a good example. When I need an example off the top of my head, I can't think of one. I'm trying to think of an example. Maybe you've had a teacher correct your logic and said you need to work it backwards. I'm trying to think of one off the top of my head and I can't think of one. It's like you're assuming what you want to show right at the beginning. Like if you, okay, let's not do this. If you wrote this equation right at the start of your proof and said, is this equation true? And you work backwards to this, that would be backwards logic. If you work backwards to this and said, hey, yes, it was true because this is true. That's faulty logic, okay? You got to start with what you know is true and work toward what you want to show. So sometimes that means reversing your scratch work. But in this case, we know this is true. These other things follow. It's fine. Okay, but oftentimes you have equivalencies and you therefore can go backwards. That's what I'm trying to say. If you need to go backwards in a certain situation. What's an example of some centralizers in a group? Well, let's go back to our D3 example. The centralizer of the element R0 is fairly easy to figure out. Centralizer of the identity in any group, in fact, is what? What commutes with R0? The whole group, everything does. And that works in any group, whether the group is abelian or not. And by the way, I hope it makes sense, quickly thinking about it, in an abelian group, the centralizer of any element is the whole group. Because the group is an abelian, everything commutes with everything else. So this centralizer idea only has significance for non-abelian groups. And it really only has significance then for centralizers of elements that are not the identity. Centralizer of R120. What commutes with R120? Certainly the identity does. Anything else? The centralizer of any element also always contains powers of that element, though it's possible powers are only that element and the identity if it has order 2, right? If A has order 2, then A squared is E, A cubed is A to the 4th is E, if A has order 2. But A commutes with itself, R120 commutes with itself, so the centralizer's got to contain R120, and it's got any power of A commutes with A. Any power of R120 does. What's a distinct power of R120 that's not written yet on this line here? R240 does, yeah. R240 is R120 really composed with itself. We can think of it as a squaring operation in the group. How about V, D, and D prime? Do they commute with R120? R120 times V, or composed with V, is D. V composed R120 is D prime. V does not. Neither does D nor D prime. And the same kind of thing happens with R240. There is the centralizer of R120 and R240. And that is a subgroup of D3, right? That's the subgroup of just rotations. Is that a cyclic subgroup of D3? We talked about cyclic groups a little bit last Friday. What was a cyclic subgroup of a group? It had a generator. What did that mean? Find it in your notes there, Macy? Did you find it? Yeah, the powers of A. You got the pointy brackets I saw you trying to make. Yeah, this is the cyclic, same as the cyclic subgroup generated by R120, all the powers of R120. It's also the same as the cyclic subgroup of R240. These elements, R120 and R240, are both generators of this subgroup because all the elements in the subgroup are powers of both things. R120 squared is R240, R120 cubed is R0. Same with R240. R240 squared is actually R120. And R240 cubed is R0. How about the centralizer of V? Well, V commutes with itself, so this contains R0 and V for sure. Anything else? What's V cubed? V cubed is V. Yeah, V generates a subgroup of order 2, R0 in itself. Same with D and D prime. Does anything else commute with V? We already saw R120 and R240 didn't. Do D or D prime commute with V? Yes or no? Assuming I didn't make any mistakes. I'm pretty sure these are all right. Go ahead, Michelle. No. The centralizer of V is just R0 and V, which is also the same as the cyclic subgroup generated by V. Centralizer of D is just R0 and D, same as the cyclic subgroup generated by D. Centralizer of D prime is just the identity and D prime, same as the cyclic subgroup generated by D prime. What's the cyclic subgroup generated by R0, by the way? Supposed to be easy. What are all the powers of the identity? Just itself. Cyclic subgroup generated by R0 is just the trivial subgroup R0 by itself. So none of these things are equal to the cyclic subgroup generated by R0. That would be a mistake to write that, even though R0 is in all of them. Let's go back and think about those permutation groups now. So again, this is a preview of chapter 5, but I think it's good to get a preview of chapter 5 ahead of time so that we can handle chapter 5 better when we get there. Let's think about S3, although I don't remember for sure if I used that notation or not. S3 is the sum of all permutations of a group of 3 objects. I called the 3 objects C3 before. That's not standard notation. I used 1, 2, 3, but it's really 3 objects. Any 3 objects will do. They can be letters A, B, C. They can be numbers 1, 2, 3. They could be other numbers 7, 18, 25. They could be colors red, blue, green. Any 3 objects or ideas can be permuted by S3. S3, it's a permutation group. Its name is the symmetric group on 3 objects. That's standard notation, S3. C3, that's not standard notation. It's just something I made up. These are the objects that I'm taking. This is the set of all permutations of 3 objects. But what are permutations? Really, they're functions. I mean, informally, we think of them as reorderings. I've got the numbers 1, 2, 3. I reorder them, say, as 2, 3, 1. So informally, you say it's a reordering, just like in discrete math and in prob and stats. Formally speaking, that's really a function. By saying 2, 3, 1, I have mapped 1 to 2, 2 to 3, and 3 to 1. When I say 2, 3, 1 in that order. The set of all 1 to 1 and onto functions. In fact, they're not just any functions. From a group of three objects to itself. Okay, we'll go ahead and take this particular list of three objects, these numbers. Again, the C notation here that I'm using is not standard. It's just something I made up. But the S notation is standard. When we did this last week, what was it, last Wednesday, I think? We used cycle notation to represent the permutations. I was thinking of them as permutations of the vertices of the equilateral triangle when we talked about D3. Right, that was the context. We were looking at this picture here. And I was thinking about permuting the vertices. So my set of three objects was really the vertices of the triangle. I labeled them 1, 2, 3. Another notation for such functions draws them as arrays, matrices, you might say, though when you draw these matrices, you don't think of them in the usual way you think about matrices. You draw them as matrices with two rows. The first row, which is the elements of C3, 1, 2, 3 in this case. The second row of which is the elements that each of these things get mapped to. The identity permutation maps everything to itself. So 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 3. How many permutations are there going to be here? Think about discrete math. Think about permutations in prob and stats. Think about factorials, or maybe the counting principle. How many permutations are there going to be here? 6, yeah, 3 factorial. Because you got 3 choices for what 1 gets mapped to. Once you've chosen what 1 gets mapped to, since the function is 1 to 1, 2 has to get mapped to something else in a given permutation. You only have 2 choices left. Once you've chosen what 1 and 2 get mapped to, you've got the choice for 3 is determined. It can only get mapped to whatever's left over. So 3 times 2 times 1, 3 factorial, or 6 possible permutations in S3. You could swap, 1 could get mapped to 2, and 2 get mapped to 1, and 3 get mapped to itself. 1 could get mapped to 3, 3 could get mapped to 1, and 2 could get mapped to itself. 2 and 3 could get swapped, so to speak, and 1 could get mapped to itself. One could get mapped to 2, 2 could get mapped to 3, 3 could get mapped to 1. That was the one I mentioned verbally a few minutes ago. Or finally, 3 could get mapped to 3, or 1 could get mapped to 3, 2 could get mapped to 1, and 3 could get mapped to 2. These are matrices, 2 rows and 3 columns, 2 by 3 matrices, but we don't think of them as matrices in the usual way. We don't multiply them or add them. We compose them because we're thinking of them as functions. And in fact, just like with cycle notation, if we put 2 permutations next to each other, say these two, we'd be thinking of those as functions that we are composing from right to left. So using this array notation, the top is always 1, 2, 3. Going from right to left, first 1 gets mapped to 2, but then 2 gets mapped to 3, so ultimately 1 gets mapped to 3 in the composition. Here, 2 gets mapped to 3, but then 3 gets mapped back to 2, so 2 gets mapped to itself in the composition. 3 must have to go to 1, right? Because this function is supposed to be 1 to 1 and onto. And yeah, if you compose them here, with this one, 3 goes to 1, but then 1 goes to itself. So ultimately 3 goes to 1. So the composition of these two permutations is this one. Compose these two, you get that one. If you compose, it's not commutative. If you compose them in the other order, you're going to get something different. Let's compose these same two permutations in the other order. Right to left. First one gets mapped to 1, but then one gets mapped to 2, ultimately. Here 2 gets mapped to 3, but then 3 gets mapped to 1. So ultimately 2 gets mapped to 1. The only possibility here in this last spot is 3 getting mapped to itself. Double check it. First 3 gets mapped to 2, then 2 gets mapped out back to 3. So ultimately 3 gets mapped to itself. And you can see these are not equal. So sideways not equal to sum. So this group of 6 elements is not abelian, which makes sense. Function composition in general is not abelian. I mean, there are some cases where functions composed will commute, like composing a function with itself, for one thing. That is array notation. However, we usually like cycle notation better. Let's go back to cycle notation. In cycle notation, I'll put the cycle notation versions of these things underneath them. That one's the identity. I could write it just like that, or like this, or like this. Any way you write it is fine as a cycle, as one of those. It just means everything gets mapped to itself. With this one, 1 gets mapped to 2, 2 gets mapped back to 1, and 3 gets mapped to itself. You write 1, 2, or 2, 1. 1, 2 is the same as 2, 1. These are different as, you might say, 1 by 2 matrices, but as cycles representing the same permutation, they are the same. They're equal functions. They represent the same function. With this one, 1 and 3 get swapped and 2 gets mapped to itself. I could write either this or this. Similar kind of thing with this one. Right, equal signs. I've kept almost making the mistake of putting these things next to each other. No, they're equal. If you put them next to each other, then you'd be composing them, and you don't want that. And here you've got longer cycles, you might say. 1 gets mapped to 2, which gets mapped to 3, which gets mapped back to 1. Remember how this works. Within each cycle, you move left to right. 1 gets mapped to 2, 2 gets mapped to 3. But then when you get to the end, you go back to the beginning. 3 gets mapped back to 1. This could be written in 3 ways. This is the same as 2, 3, 1, and it's the same as 3, 1, 2. All 3 ways are valid ways of writing this permutation in cycle notation. They represent the same function. Similar kind of thing with this one. But notice these things are different. These 2 things are different here. Which of these elements do you think, if any, have order 2? When you square them, compose them with themselves, you get the identity. Do any of these have order 2? The whole group has order 6. 2 does divide 6. It's possible some of these have order 2. Anyone want to say? You want to say? Yeah, the old ones with only two entries, so to speak, in the notation. You compose this one with itself. If you're unsure, you can write it down. 1, 2, 1, 2. Writing it next to itself like that means you are composing it with it yourself, squaring it if you like. But that squaring represents composition, not multiplication in the usual sense. How would you think about it? Start right, go right to left. 1 gets mapped to 2. But then, hey, you go to the left here, 2 gets mapped back to 1. With 2 starts off getting mapped to 1, but then, hey, it gets mapped back to 2. And both times 3 gets mapped to itself. That's the identity. Another notation used for the identity is an epsilon in this context, since epsilon is the Greek version of E, and we often use Greek letters to represent permutations. Similar kind of thing would happen with 1, 3, and 2, 3. Square those, you're going to get the identity as well. They have order 2. Hey, maybe this is not so surprising. There's 3 elements of order 2, just like in D3, there were 3 elements of order 2. And that's how I introduced these permutations, is thinking about D3 that way, right? This is going to be isomorphic to D3, the dihedral group, symmetries of an equilateral triangle. These 2 elements are going to have order 3. Double check it. 1, 2, 3 cubed. I mean, we could do square first, but let's go ahead and do the square first. That's worth doing anyway. 1, 2, 3 squared. Compose this with itself. Work right to left with the composition, but within each cycle, go left to right, except when you get to the end. First, 1 gets mapped to 2 with this function on the right, but then 2 gets mapped to 3, so ultimately 1 gets mapped to 3. Now think about 3. 3 gets mapped to 1 under this permutation, but then 1 gets mapped to 2. So ultimately 3 gets mapped to 2. 2 must have to get mapped back to 1. That's got to happen, but it's probably worth double checking to make sure you didn't make a mistake. First, 2 gets mapped to 3 over there on the right, and then 3 gets mapped back to 1. So 2 does get mapped to 1. Yeah, and that's the other element of order 3. It's got to be. And 1, 2, 3 cubed. I can think of as 1, 2, 3 squared, which is 1, 3, 2, composed with 1, 2, 3, or the other order. This should be the identity. Check it. First, 1 gets mapped to 2, then 2 gets mapped back to 1. Next, 2 gets mapped to 3, but then 3 gets mapped back to 2. Finally, 3 gets mapped to 1, but then 1 gets mapped back to 3. Every element ultimately gets mapped to itself. You can write that. 2 elements of order 3. Yes, S3 is isomorphic to D3. And we write, you write it like it's an approximately equal to. Actually, that notation is not always used. Sometimes you'll see people write something more like this. Some people write it like this. Some people maybe just write it with 1 tilde, just to save time. All those different notations mean the same thing in this context. They mean S3 is isomorphic to D3. It doesn't mean it's approximately equal. They are different groups. They're defined differently. Though one thing they have in common is in both groups, the elements are really functions. But in D3, the functions are functions on the entire plane, really. Rotation of the entire plane, reflection of the entire plane, or just the triangle if you prefer. Whereas these are functions, one-to-one and onto functions from a finite set to itself that I'm calling C3. Again, that notation is not standard. But the S3 notation is standard. Excuse me. Let's end class today by starting to think about a more difficult symmetric group. We will definitely not make a Cayley table for this. Well, it's worth starting to think about anyway. Not even going to list out all the elements. How about a symmetric group on 4 elements? I could say C4 is the set 1, 2, 3, 4. That, again, is not standard notation. Just made it up. But this is standard notation. S4 is the set of all permutations on 4 objects. It's called the symmetric group on 4 objects. Technically speaking, it's the set of all one-to-one and onto functions. Say from C4 to itself. Actually, since I'm considering C4 to be a set of numbers, technically speaking, if I considered a different set of 4 objects, say 4 animals, dog, cat, horse, pig, the set of permutations on 4 animals, technically speaking, you would say that's a different S4 because the functions are different, right? The objects are different. But of course, it would be isomorphic. So it's simplest just to think of your objects as being numbers. So I could use the array notation if I like. But now they'd be 2 by 4 matrices, 1, 2, 3, 4. Here's an example. I could map 1 to 2, 2 to 3, 3 to 4, 4 back to 1. In cycle notation, do the natural thing. It would look like that. And I hope it makes some intuitive sense without checking it. This probably has order 4. And it does. You could check it. On the other hand, I could, for example, keep the 4 fixed and just permute the 1, 2, and the 3 like this, 2, 3, 1. And then in cycle notation, it would look exactly the same as an element of S3, but it really would be a different thing. It really would be an element of S4. It would map 4 to itself, but the notation would be the same as the element of S3 that map 1 to 2, 2 to 3, and 3 back to 1. So really, in a sense, that means the array notation is superior in terms of being more precise about what exactly is going on. You have to know from context that this is an element of S4 when you write it in cycle notation. Yeah, I have to say, hey, this is in S4. Since you don't see a 4 in there, that means it keeps 4 fixed. 4 gets mapped to itself. And that would have order 3. Then you could have elements of order 2, for example, like this. What if I did this? Can I write that as a cycle? 1 and 3 are sort of swapping places, and 2 and 4 are sort of swapping places. Can I write that as a single cycle? No, you can't actually. This is a different kind of thing in cycle notation. You can't write it as a single cycle, though you can write it as a composition of 2 cycles. You could write it as this cycle composed with this cycle. And it should make sense by symmetry. I mean, these are just arbitrary symbols anyway. you should be able to write those in the other order. But the function composition is still right to left in both cases. Evidently, these things commute. Doesn't mean the entire group's abelian. It's not. But these things commute. 1, 3 commutes with 2, 4, and vice versa. They would be elements of the centralizer of the given element. How many elements total would there be in S4? Yeah, 4 factorial, 24. We have just written down 4 of them. The Cayley table, the main body would be 24 by 24, 24 squared things to figure out. Of course, many of them would be easy, but that's still a lot. What's that, 576 or something? Is that right? 24 squared. Yeah, 576. There'd be 576 elements in the main body of the table to figure out. Again, with the identity, that could go quick, but with all the other ones, it would take a lot. It would take you quite a while to write down the Cayley table. Oh, doesn't that sound like fun though? Like a fun project? You could make it artistic even. You could make a beautiful Cayley table for S4. Maybe spring break, if you got an artistic side to yourself. Picture, maybe make a painting of the Cayley table for S4. So there's elements of order 4 in S4. There's elements of order 3, elements of order 2. Obviously, the identity is order 1. The entire group has order 24. All those numbers, 1, 2, 3, 4, do divide 24. So you might wonder then, does it have any elements of order 6 or 12 or 24? Is it cyclic? Is D3 cyclic? S3? Is that a cyclic group? Any generators for the whole group? Can all the elements be found by doing the powers of a single element? No. And in fact, if you think about it, cyclic groups are those whose elements are all powers of one element, a generator. Cyclic groups have to be abelian, don't they? Because powers of an element all commute with powers of that same element. Every cyclic group is abelian. So if you've got a non-abelian group, it can't be cyclic. You see how we're starting to figure out some things about the structure of groups? All this just from the axiom, so to speak, the definition of a group as being closed, having a binary operation, associative property, existence of an identity, and existence of inverses. You can figure a lot out. It's amazing how much you can figure out just from those basic things. Every cyclic group is abelian. Therefore, the contrapositive, every non-abelian group is also not cyclic. S3 is not cyclic, S4 is not cyclic. So no, what that means is there's in S4, where'd S4 go? In S4, there can't be an element of 24, order 24, because if there were, it would be cyclic. And in D3 and S3, there can't be an element of order 6, because if there were, it would be cyclic. And therefore, it would be abelian, and it's not abelian. Could there be an element of order 6 or 12? Well, we haven't ruled it out yet. I claim there's not an element of order 6 or 12. The only possible orders are 1, 2, 3, and 4. I by no means have proved that. It does have subgroups of order 6 and possibly order 12. Possibly. definitely order 6 because it's got subgroups that are isomorphic to S3. Consider all the subgroups where 4 gets mapped to itself for all the elements. That would be isomorphic to S3. Or consider all the subset where 3 gets mapped to itself for all the elements. That would also be isomorphic to S3, or 2 or 1. So it's got subgroups of order 6 that are isomorphic to S3, but those are not cyclic subgroups. There's no elements of order 6. Again, I haven't proved that, but that's something you can take to the bank. We're discovering things. This is like a process of discovery. One more quick example to share with you. I'm not going to go through all the details of this. Maybe we'll look at it more on Wednesday. Let's see, where did I put it? Oh, I called it class 5. I was originally going to do this last week, but didn't have time. Call it class 7 now. Got a bunch of matrices here, 6 matrices. That's really annoying having that door there. 6 matrices. What do I want to do with these matrices? Notice the entries of these matrices are all 1s and 0s. I'd like to multiply them mod 2. How can that be done? Well, multiplying in general, say D times F in Mathematica must be done with a period. And if you want to see it as a matrix, you can do / matrix form at the end, or you can do it at the beginning. So there is D times E as an ordinary matrix multiplication. But if you do mod D times E comma 2, it's going to mod everything by 2, and 2 mod 2 is 0. And that D times E is another element here. It's F. These are all the 2 by 2 matrices whose entries are either 0 or 1 and also have non-zero determinant. You can make other 2 by 2 matrices with 0s and 1s as entries. In fact, there's 2 to the 4th or 16 such matrices you can make, but only these 6 of them have a non-zero determinant. These are the elements in the GL, general linear group. GL stands for general linear group of 2 by 2 matrices with entries not in R or in Q or in Z, but in Z2. And saying it's a general linear group implies the determinant is non-zero. And the operation is multiplication. So we have A, B, C, and D are all elements of Z2. And the determinant AD minus BC is not equal to 0 mod 2. That means you could say it does equal 1 mod 2. And multiplication is done mod 2. Multiplication mod 2 is the operation. It's the group operation. You need to assume the determinant's non-zero, otherwise it's not a group under multiplication. It would be a group under addition, actually, if you allowed the determinant to be 0. That becomes a group under addition, then that's a group of order 16 in that case. But this is a group of order 6, and those 6 matrices. We'll play around with it a little bit more on Wednesday to explore that group. Okay, have a good day.